Thank you all for being here today to listen to this presentation in the paper Self-Supervised Learning with Data Augmentations. Probably isolates content from style. This paper is from the authorship of Julius von Kügelgen et al. And was presented at the Lyrics 21. But before diving into the details of the paper, let's talk a bit about self-supervised learning. So self-supervised learning is a form of unsupervised learning where supervisory signals come from the data itself. In natural language processing and speech recognition, a successful approach has been to predict some part of the observation from another. For example, we could predict the future from the past or original from corrupted. In computer vision, there are similar approaches where we can, for example, solve a jigsaw puzzle to reconstruct an input image. We can also color a grayscale image, or we can reconstruct some part of the input that has been masked or corrupted. But another approach is called the joint embedding self-supervised learning methods, where we try to approximate the representations of different views of the same observation. So here, given an image from an unlabeled data set and a set of transformations, what we do is to apply two different transformations to the same observation to generate a pair of augmented views. Then, joint embedding self-supervised learning methods will consider identical or related nonlinear functions, typically deep neural network encoders, and these encoders will map our two views to a lower dimensional representation space. The optimization process then becomes learning the two encoders such that the similarity between the latent variables of the two views is large according to some similarity metric. These joint embedding self-supervised learning methods have advantages over other approaches because they don't require us to reconstruct the high-dimensional data. But the challenge is the collapse mode, where the encoders will output a degenerate solution that trivially maps any observation to the origin. So in other words, what happens is that each encoder will output a constant feature vector, non-informative feature vector, regardless of the view that is being fed to the model. There are several strategies to prevent collapse that we categorize into contrastive learning, distillation methods, and regularization approaches. In contrastive learning, the main idea is to approximate the representations of positive pairs in the latent space, but to push the representations of different views apart. With distillation methods, on the other hand, what we try to do is to distill knowledge from one model or from one model head to the other. For example, in simple CMEs neural networks, we have a predictor network aside from the projector, and what we want to do is to approximate the predicted representation of one embedding given the other embedding to the embedding we are trying to predict. And finally, with regularization approaches, what we want to do is to reduce redundancy in the latent variables. And so, for example, with variance-invariance covariance regularization, what we can do is to increase the variance along the batch dimension so that different images have a different representation, or we can also minimize the off-diagonal elements of the covariance matrix of the different views, so that there is no redundancy along the feature dimension. And so, given these joint embedding self-supervised learning methods, what this paper tries to do is to understand if these methods with data augmentation can reveal or uncover some properties of the underlying data generation process. So what we want to understand is identifiability. So given an observation, there is an infinite number of generative models that could have generated our observation from the same latent variables. So without any assumptions, it becomes impossible to identify the latent variables. So in this work, we make a set of assumptions and then try to understand if we can achieve identifiability. Just to formalize a little bit this problem, we have an observation x, and we assume it is generated by a smooth and invertible mixing function f on the latent variables. And so to generate the augmented view, we will apply the same or a related function to the transformed latent variables, and then we will obtain the augmented view. From the other perspective, we can understand that to obtain the latent variables, we can apply the inverse of f to our observation. So what we assume here is that we have data augmentations that will preserve certain parts of our inputs. So with this assumption, we can then state that the latent variable vector can be partitioned into two disjoint parts. We assume that we will have an invariant part, which is the dimensions of the latent variable vector that will remain constant despite of the data augmentation, and it is shared between the two views, which we refer as content. And we also have a variant part that will be different among the two different augmentations that we refer as style. In this work, we then assume that the latent variables is a combination of content and style. And so, in comparison with other works that try to also understand identifiability, in this work we have a more relaxed assumption, and we allow some causal dependencies in the latent variables vector and non-trivial statistical correlations. So we can also understand this from a structural causal model perspective, where data augmentation can be viewed as latent style interventions in this structural causal model. So we here observe that the views are affected by content, and that content can affect style, but style cannot affect the content partition. And so what we then try to do is to infer content from the views that we have. And we say that the content partition is block identified by a function g if the inferred content contains all and only information about the content. So with this formal and previous assumptions, it then becomes possible to block identify the content partition in both generative and discriminative settings. In today's presentation, I'm going to focus on the discriminative self-supervised representation learning setting, but you have access to the paper that you can then later review to understand the proof of the generative approach. So if we have guarantees that the encoder function is a smooth and invertible function, then minimizing the alignment between the two latent variables is enough to ensure that we have invertibility. But imposing invertibility in our encoder imposes many constraints to the architecture that we choose. And with high-dimensional data and real-world data sets, it becomes challenging. So the need comes to bridge the theory with practice. And so an alternative approach is to minimize the alignment between the two views, but subject to the constraint that we maximize the entropy in the latent variables. So with this approach, we then consider two objective functions to study identifiability. On the one hand, we have simple contrastive learning of visual representations, which considers the information noise contrastive estimation loss that tries to approximate the representations of positive pairs using the cosine similarity, and to push the representations of negative pairs apart. This loss can be understood as an alignment loss with approximate entropy regularization. And it is related with so it provides a lower bound to the mutual information between the two views. On the other hand, with the Barlow-Twins loss, we have regularization methods where we try to reduce redundancy in the embedding space. So what we do is, on the one hand, we will maximize the diagonal elements of the correlation matrix between the two views and minimize the off-diagonal elements of the correlation matrix such that we reduce redundancy. And here, reducing redundancy in the embedding space is also related to increasing entropy, which means that the previous theorem that we have discussed, so that the inferred content must contain all and only information about the content partition, is a valid theorem here. So to empirically evaluate these concepts, the authors propose a benchmark dataset for evaluating identifiability, which is called the causal 3D ident. This dataset consists of 2024 times 2024 images that were rendered from 10 latent variables, and it represents 7 classes. We have 7 variables to represent, 3 variables to encode position, 3 variables to describe the rotation of the object, 2 dimensions to represent the hue of the object and the scene, 1 variable to describe the position of the spotlight, and another variable to describe the color of the spotlight. And so, having the data set, we now choose as the encoder, so as G, a ResNet 18 encoder. And we also have a fully connected layer with leaky real non-linearity to estimate the content partition from the latent variables. And here we consider the simple contrastive learning approach. But as the number of content variables is unknown, the authors chose to fix it to 8. They also demonstrate that the results are robust to the choice of the number of content variables that we select. As data augmentation, the authors do a controlled experiment setting where they vary types of data augmentations at a time. And the idea here is that we will choose data augmentations that will only affect some specific features of our input image. We have crop, resize, and flip data augmentations that are focused on transforming the position of the object and also will affect somewhat the rotation. And we also have color distortions and rotation. Then we define a causal structural model to modulate the dependencies here, where we can see that the object class is a cause of the position of the object, the rotation of the object, and the hue of the object. But then there is no causal dependency between the positions of the spotlight and the backgrounds and spotlight hues. As another experiment, the authors also do latent transformations. So instead of augmenting the image, they then do latent transformations on the latent variables vector and try to infer the content partitions from the transformed latent variables. And so we here have the results of the experiments they performed. So they evaluate this approach in 2 different ways. On the one hand, they try to predict the class of the target class from the inferred content partition. On the other, they consider a linear logistic regression on the inferred content to assess if it is possible to predict the generative variables of the images. So, for example, here, I cannot point, but you can see that in the first experiment, they performed color distortions, and we can see that the class prediction the accuracy is a little bit low, but then we can see that we can accurately predict regress the position of the object and the rotation variables, but then the inferred content does not contain information about other spurious variables like the color. In the second row, we will affect the position of the object, but preserve the color information. And we can observe that the inverse happens. So the position variables are affected, but not the color information. And then we can also observe that the best results are obtained by a combination of position and color transformations, where here, in the crop and color distortion transforms, we can see that the position of the object is mostly preserved, and we discard color. And we also preserve colors, which are the spurious variables. So if you see the structural causal model on your right, on your left, the hue of the background in the spotlight and the position of the spotlight that should not affect the class. But here we have that the hue of the object is preserved. Now that the position of the spotlight is somewhat preserved, but it has some certain correlation with the class variable, because if the position of the object influences class and the position of the spotlight influences the position of the object, then there is somewhat a certain correlation between these two variables. So, but another interesting thing we can observe from these results is that it is somewhat challenging to select data augmentations that will accurately affect only a specific subset of latent variables. And another interesting observation that we make here is that the content style partition is directly dependent on the set of data transformations we choose. So this is here resumed, but finally, just to discuss another property towards implementing this paper in practice, the assumption that only the content variables is predictive of the target is a hard assumption, because in certain downstream tasks, style variables might be highly correlated with our target class, so they might be of interest to preserve. So not all style variables should be discarded in these joint embedding self-supervised learning methods. And now I would like just to give a few ideas on how to apply these methods to several tasks. So the main application here would be label efficient learning. So in many settings we have large unlabeled data sets, but only where a subset of the data is annotated. So we could use these joint embedding self-supervised learning methods, and in particular the content style partition disentanglement, to learn features that are discriminative of our target class without any supervisory signals. On the other hand, we could also extend this to multitask learning. For example, an idea could be to consider two content partitions and one style partition. And where these two content partitions, one of them would be task-specific, and the other would be shared between the two tasks. And so, in these joint embedding self-supervised learning methods, we could try to disentangle the exclusive and shared content partitions from the style variables. The same is applicable to domain generalization issues. We can also have shared content between domains and variables that are domain exclusive. And of course, invariant representation learning, where we are trying to induce our model to be invariant to certain features of our image, for example, to the scanner that was used to digitize a magnetic resonance image. So overall, the main idea that I want to transmit here today is that this is like a causality-inspired representation learning machine, where what you need to do is to define a structural causal model to represent the latent style interventions, and then exploit the properties of this structural causal model as inductive bias to derive a content style disentangled representation, and that could be useful for our desired application. So this is it. Thank you for listening to this presentation today, and now I am available to listen to your questions and discuss any ideas you might have.